speaking on our program Science Yield Improvement via Onboard Prioritization and Summarization of Information Systems, which we like to call SYNOPSIS. So SYNOPSIS is focused around onboard science instrument autonomy. So this is looking at mission cases where you have an instrument that you want to do some sort of processing on board. That could be because you're generating so much data that you can't send it all down. It could be because you're looking for transients and you want to be processing it on board to see if you see it, and you only want to allocate the bandwidth if you actually capture the phenomena you're interested in. It could be trying to do onboard calibration of data to make follow-on decisions, or a wider number of things that are starting to become common in mission systems now. And so I'm going to go through three just to kind of lead this conversation off with kind of what we're trying to facilitate here. First one is an instrument program we're just working on called OWLS. So this was a number of instruments that are focused around life detection on icy worlds. So we have one that's a digital holographic microscope. Can you see? Sorry. Yeah, you can see it in the top right. So that's a digital holographic microscope data. So it's being generated about a gigabyte a minute. So you're looking at icy world missions where you may get to send back 100 megabytes across the whole mission. The question is, how do you go from hundreds of gigabytes down to 100 megabytes while keeping all your science? On the bottom, we have a mass spectra that's coming out of a mass spectrometer. Same thing. You're starting to look for compounds that may be indicative of life, and you have a cross-correlation question across these instruments. We just call it the podium test. Who's going to stand behind a podium from NASA and say they found life on another planet? Right? You want multiple streams of evidence to be able to justify this, and the OWL suite could do that if you can get down the correct data from the different instruments and be able to have a cogent story while distilling 10,000 times down on your data. Things where compression is not going to be enough. And this was one of our driving use cases for building a system like SYNOPSIS. We built this system outside of SYNOPSIS as kind of a N=1 example, and we have a few more that our group has done over the years. And something that we're finding as a challenge is being able to bring these systems from kind of this bespoke, my bias here is I'm more of an algorithms developer, more of a data scientist, and we write flight software as a function of getting on board a mission that's not our background. So we're trying to be able to bridge that gap between, flight software community, the algorithm community, and how can we make this easier to kind of get these algorithms on board, increase our technical readiness level to the point where it's easy to kind of be picked up by a mission and kind of facilitate that whole effort, as well as reuse. Another one that I'll just quickly allude to, this is from a mission called NeoScout that we just flew on EM1 on Artemis. So you can see in the bottom left, this is raw data. This is actually data from Rosetta coming in. But you can see how messy it is. So through our pipeline on board, we're able to do onboard calibration, and then finally jumping data sets, but that's New Horizons data, that's Pluto and Charon. So how do you go from 2 gigabytes of data to about 1 megabyte of data on board, find your target, downlink just that data? The real limit on this mission was that we, our small CubeSat interplanetary, we had kilobit per second downlink scoped, and not much DSN time. So, again, how do you do all this data processing on board? Another one that we've deployed, this was on MER, MSL, Mars 2020. It's a system called Aegis that our group developed. So this is basically finding the rocks in an image and then shooting the best rock with the ChemCam laser. Best is a can of worms. We can get into that in a different time. But, basically it's looking at the rocks. It's filtering out ones that don't meet some engineering criteria, and then it's scoring in against the rocks that are potential candidates from an engineering perspective, picking the features that identify it as the rock that's most interesting. And this is all when ground is not in the loop. So this is a big concept with all of this. It's, if you have humans and the humans can talk to the spacecraft, you use the humans. We like to call this, human on the loop. What do you do in the times between when you could talk to the spacecraft? Whether it's, a flyby scenario where you're just not going to have the opportunity to talk during the flyby, or you're just far away and your ground in the loop cycle is very limited. And the idea here is SYNOPSIS is meant to be kind of a framework to facilitate all of these different types of algorithms. Think of it as a catalog of algorithms that are facilitated through the SYNOPSIS framework, giving kind of standard practices for how to write these algorithms, how to integrate them into SYNOPSIS, and then SYNOPSIS kind of being your bridge into your actual flight software environment. So, I gave 3 examples that we've done, but the idea is to add a big catalog of these. And so that when a mission starts, if you want to do onboard data prioritization of multispectral data, right, you could check the catalog. Has somebody done this before me? Can I start with their code? Can I modify as needed? Right, it gives you an incentive to stick to standard formats. It gives you a starting point brings that requirement to use some of these systems down, especially for smaller missions. And so some of the other ones we've thought about are things like feature identification, right? Being able to identify features on board, potentially prioritize that data, for specific downlink. Things like compression, right? It's always tough to pick the compression ratio you want before you get to see the data. So on board, can you build a small system that checks the residuals of the data compression at different rates and then identifies, which one has the best residuals around the science you care about, and then prioritize data that way. Like I mentioned before, transient detection. We do a lot of stuff looking for things like plumes, dust devils. You can't command an image to take a thing where you don't know where it's going to be. There's also aspects for instrument health monitoring. So, being able to look and see which data doesn't look right and, de-weight that for prioritization for downlink, as well as some novelty, diversity sampling. So how do you only send the data? You can basically tune this on the ground. Am I interested in more data that looks like the data I have? For use cases where you want to bolster your argument, right? You've seen it once, I want to see it again. Send me all the data that looks like the data I've seen. Or do you want the opposite? Do you want to see all the distribution of data that you potentially have access to? Send me all the data that doesn't look like the data I've already seen, or a mixture of both. And SYNOPSIS kind of provides that framework at the top level to help you do things like that so that you don't have to try to bake it into your algorithms. If your algorithms can generate standard outputs that can connect to SYNOPSIS, SYNOPSIS connects to your flight software, it makes this whole situation a lot easier. And so, as I mentioned before, SYNOPSIS has some kind of standard capabilities that we're talking about: cross-instrument data prioritization, single instrument data prioritization, prioritization between science utility or diversity. It allows you to do onboard science triggers. So if you see the thing you're interested in, maybe you have a different instrument you want to do a follow-up observation with, we don't do the whole dynamic replanning, rescheduling, but it can be a trigger that goes into that dynamic replanning system that says, I've seen something that's uncommon, I should now take these follow-on steps. And I think the biggest one for me is streamlining that integration of these sorts of algorithms into the flight software environment. We're going through a period where missions are, instead of, in the end of phase E saying, sure, try it, right? Our risk posture has changed to now starting to baseline these types of things. They want to know, what kind of compute do you need to run these heavier algorithms? What do you need? We just keep saying, just laptop in space. I don't know how to think about the kind of flight software architecture questions, right? That's not in our background. So we're trying to take that plunge for our community to kind of get closer to your community. And so when we talk about SYNOPSIS, kind of internal to SYNOPSIS as a brief architecture, we like to call, each of these pipelines that we've talked about, we call them autonomous science data systems. So for a given type of instrument, what type of standard processing do I do? What type of outputs do I generate? Store that in a database. Data comes in from all your different types of instruments. You do your standard processing for each instrument. You store it in a database. And then when it comes time to do downlink, you can run your prioritizer, which, like we said, has a distribution that you can set between diversity of data and more data that looks like a certain type. So kind of keeping that prioritization decision independent from your data processing. And so for that data processing, the kind of interface that we have on these different algorithms, we define 3 key metrics on each of these pipelines. The first is what we call a science utility estimate. And that can be a loaded term. Talk to a scientist, how do I say what has scientific value? And that can be hard to encode in a single function, but the goal is to encapsulate the things you already know. So we were talking about that digital holographic microscope. That's sucking in water. It's looking for critters swimming around in this volume. And basically what we want to do there is cut out mug shots around the data, these critters swimming around. The rest of it's just background. We don't really care about that. So a science utility estimate for that kind of data could be, how many little critters can you count? How many things are moving between tracks? Basic things like that are your first order heuristic of if I'm going to care about this data. And if you really look at your science use cases, you can start to come up with some of these things, and you have to come up with some objective function that defines how much you care about each of these things and come up with a floating point value that represents it. Similarly, we do a data quality estimate. So this is if you can onboard, you can check some of your data for known issues, right? Jitter, blackout, right? That image that was, only half there, right? If you have known standard things that are going to impact the quality of your data, can you just filter those out? So, for each of these bits of data you're defining, I think this data has a lot of scientific value. And, does this data look right? Does it pass all the kind of standard checks? Maybe it's contrast on an image or something like that, signal to noise, right? You encode all of those things in a standard floating point value that allows you to represent that data more concisely. And the last is a diversity descriptor. So, what key things are you checking for each time that you would then use to compare against your database of other observations and say whether this looks like data I've seen before and kind of fits into known categories or is potentially unique. And we track each of these 3 metrics for each of our ASDSs, put that through SYNOPSIS, and then SYNOPSIS basically gives a list back to the flight software of what data you should prioritize in what order. So then for actually looking at how this architecture fits in with the larger flight software package, we've so far talked about what we would call the SYNOPSIS core library, which is a C++ implementation that basically takes data in the front. You define the ASDSs for each of your different instruments. It provides the database storage. It provides the data prioritization algorithms and a number of other things we'll talk about. And then you got to write those ASDSs for your different instrument types, or potentially work from a catalog of existing ones. And so you really have 3 levels you have to pick here. The first is your flight software environment. And if you're using something like F prime or CFS, the idea is that we would have a component or an app for those, and those are things that are being developed now, so that you can just drop it in as a component to these kind of common software libraries. Or if you're using a custom implementation, right, you could just take your custom implementation and write the interface to the SYNOPSIS core library. This is really that glue between, your memory allocations, your timing, all those types of things, your logging. We're providing some examples, that will probably need small modifications depending on your topology, but, basic connections for F prime and CFS. The idea is you probably don't need to touch the SYNOPSIS core library unless you want to do something unique, and then you have to build those ASDSs for each of those instruments. And that's really something that we can't provide. You start with a catalog, but almost always, if you're doing a new mission, you're probably doing new science, there's probably something you'll want to add to that. So while we see it as a catalog, we see those as a catalog of starting points as opposed to, take it and drop it in. But, if you're doing something maybe at a university and you just want to be able to prioritize your data, and the science is not necessarily the core, it's learning to build the CubeSat and learning to build the flight software, maybe you can just take it and drop it right in. And so as far as for concept of operations, we see kind of 2 aspects that I think are driving this. SYNOPSIS can either be designed to be called directly from the instrument. So at the end of your command, that actually triggers your data collection. You can send a message to the SYNOPSIS component that says, I've collected new data, it's here, process it. Or you can send that through ground command. And ground command would, equivalently say, the data lives here, process it this way. And these are kind of meant to be kind of used one or the other. I think probably in practice, most people would call it directly from the instrument, and then it would get dropped in a queue to be processed. And that kind of relates to how you do this from a synchronicity perspective. Do you actually want to process the data immediately after the data is collected? One of the considerations we have here is a lot of these algorithms are computationally intensive. So you can imagine the case where you're in a flyby scenario and maybe you're not going to do dynamic replanning. You're just going to collect the data you plan to collect either way. And then kind of as a post-process, you want to figure out what's the order of data I want to collect. So something maybe like more like New Horizons, right? The data is going to be the data, but then between the flyby and the 6 months of downlink, you want to try to put it in a sorted order of quality. And so the idea there is you probably don't want to use your compute cycles during the flyby and bottleneck your CPU to be able to actually process the data. You're not going to make a follow-on decision. So, set it into a queue and asynchronously trigger that queue later to actually process all that data. You have the cycles, you have the time. You got 6 months before you're going to start downlinking. The other aspect is if you want to do it synchronously. So if you're doing a flyby and you want to process that data, make some determination based on that data, and then feed that back as a trigger back into your flight software, maybe to dynamically replan and say, that data actually looked really interesting. We saw something, we weren't really sure if it was going to be there. something like plumes on Europa, right? Maybe they're there, maybe they're not. So maybe you leave a science trigger in there, and if you ever see the plume, you then want to do trigger these 3 or 4 follow-on observations after that data is collected. So you would want to do that synchronously so that you don't realize 3 days later that you saw it. And so we're in the we support all 4 of these different configurations. So other implementation considerations that we've thought through to kind of try to bridge this, and one of the things that we would love to hear from this community too is other things we should think about. What are the other things that are going to be limiting for us to be able to infuse this? One of them is being able to connect to the spacecraft clock, so being able to pull that trigger in for timeouts and for timing all of these long-running processes. We know that they'll probably be run at a lower duty cycle just because of the amount of time they take to run. So we want to make sure that we have the correct timeouts and watchdogs and all those things to be able to do that effectively without identifying mission risk. Same thing with logging, right? We've connected it all up to EVRs and those sorts of things. And right now we have implemented that database where we talk about having to track the statistics for each data set. We're tracking that as a file-based SQLite implementation that we think should be able to fly, but we'd definitely be interested in hearing people's perspectives on that if there's better ways to do that. And right now we're still using pre-allocated heap, but that's for that core library. So the idea is you would swap that out if you're, swap that out to be pre-allocated based on your flight software implementation that you're using. And we have swapped those out for the F prime, and we will for the CFS as well. So verification, validation, this is one of the big things that we really are looking at, coming from kind of the write it on your laptop, publish a paper community. We're really interested in how do you verify, how do you validate, especially systems that are deterministic, but they're deterministic given a data input that you never get to see. So you kind of have to do this in reverse. You have to generate representative data that could flow through it and then measure your output to make sure that given any data input, you're safe. So we're looking through activities, and that's a big thing in the kind of data science onboard autonomy world, to be able to validate this, to get mission acceptance and a risk to posture that would be willing to fly something like this. So looking at making sure that we're compliant with P10 rules, to really kind of targeting Class D missions. Class D missions, CubeSats, interplanetary CubeSats are kind of that right mix of the risk posture to kind of need something like this to be able to pull off kind of the riskier mission scenarios, close the data budget, close the gaps that are just inherent with a small platform. And they have the risk posture with, lower software standards to be able to fly things that are a little bit newer. So we're kind of around the TRL 3 range now. So looking to increase that and be able to find opportunities, especially in small sats, to be able to fly this and demonstrate value for some people, and especially take some of the pre-existing algorithms we've done kind of a la carte, the bespoke allocation, the bespoke implementations that were done for things like MSL, Mars 2020, NeoScout. All of these could be converted to ASDSs and put in SYNOPSIS, or work with teams to write ones that are appropriate for their instruments and their science. One other thing we've done is, we talked about that relationship between prioritizing based on diversity or prioritizing based on raw science utility. Something that we've implemented to try to facilitate that in more complex scenarios where one instrument may have a downstream implication on the other. So, this data is actually interesting if this data saw it, between instruments, where you can't just calculate a raw value per observation and then feed it forward, because there are actually correlated relationships that you'd want to capture. So we have a whole library, a language that we've built up that's actually written on the ground and then uplinked as a flight software string that you can then define these constraints and these applications, and gets decoded on board in the application package in the SYNOPSIS core library. So you can say, if instrument 1 has has a high science utility, and instrument 2 sees a certain phenomena, that increases the science utility for both of these. That way, when that collectively gets prioritized, you're reflecting the motivation to have these two instruments be there together, right? Maybe independently they're not interesting unless you see them together. So to be able to encode those rules, to be able to update those rules in flight, we provide this syntax. This is kind of an eye chart, but this is kind of that whole language that we've identified to be able to do this. And part of this verification is being able to kind of prove this is safe to be able to decode a language like this on board. We also support different types of data prioritization. So while we have kind of both of ours, that diversity and that science utility, we also want to fit into the larger downlink posture of a mission, right? It's probably unlikely that the first missions to use this will totally want to rely on this for everything, right? You'll also have standard products you want to send, telemetry, EVRs, right? So you may have the classic kind of binned data, FIFO queues where you have, things at different priority queues and you drain each priority queue as you go deeper into your prioritization. We try to be backwards compliant with architectures like that. So being able to say, this priority bin is allocated to output from SYNOPSIS and you're allocated 100 megabytes, right? You can code that in with this very easily and say that, that 100 megabytes we're going to let SYNOPSIS fill, but it's only allocated after, the 200 megabytes of standard high priority data that we need to get, right? So, you don't have to solve the full problem in this framework if you don't want to. We've also left in connectivity for onboard planners. So if you want to take some of the outputs from this system and feed them in, like we talked about for, follow-on triggers or things like that, if you see a certain phenomena, you get a certain output from SYNOPSIS. Being able to feed that out as telemetry into an onboard planner that may, actually modify your planned activities based on that output. And so that really kind of captures what we've done so far with SYNOPSIS. We talked about that Ocean Worlds example, kind of just end with a couple more slides about some of the demonstration that we've done in this system on a recent field campaign where they went out into the field. They had all these instruments. Scientists were there. They collected a terabyte of data. And the question, sitting in the back of the van was, did we find anything? And they were, in a mono lake out in, rural California. So this was not the flight case. They didn't have to downlink all this back. But even sitting in a van where theoretically you have all the data right in front of you, scientists still had to figure out with a terabyte of data from the field, what do we do tomorrow? Right? Did we have any data that there was jitter because it wasn't set up properly, or did we find any alive swimming critters that we would want to focus in on? So even focus of attention in a laboratory environment or field environment is something where we're kind of starting to take those baby steps towards flight. Since we kind of talked about this already, but if you see in the top right that movie playing, this is a Fourier space of the digital holographic microscope compressed down. So the things moving around, some of these things are alive and they're actually moving around and you can see them, make a right turn. And, that's something that's clearly alive versus something that's just kind of floating and, that's just brownie in motion. So you can see the purple tracks are actually things that are alive. The blue tracks following it are things that are not. And this is kind of a post-process summarization of this algorithm running where, first we're doing particle identification, then we're doing particle tracking between frames, then we're actually running a machine learning classifier to actually look at some of the features that are characteristic of life and try to make a determination of which ones we think are alive, which ones we think are dead. And that's part of our prioritization, right? We don't really only care about the things that are alive, but in lieu of things that are alive, we'll take the data on things that are dead versus chamber background. So the idea is to then cut out the data around those tracks and send that down and be able to show that to scientists. These are mostly for people to look at after the fact. I just wanted to include them, but each of these different plots show a different flavor of utility. So on the left, you have diversity, where you're prioritizing diversity. On the right, you're prioritizing that raw science utility. And in the middle is kind of a balanced scenario. And the idea is you could think of this as a slider bar on the ground. So as your mission evolves, you can change your prioritization regime to say, maybe in the beginning, you want to see a little bit of everything. But then as you start to kind of refine down on what may be interesting, now you actually want to start to increase your evidence around a certain thing. So you'd go back to your rules, you'd change your rules-based system to say, these are the things I want to add weight to, and you would change your prioritization scheme to actually say, send me more of this type of data to be able to bolster your argument for the podium test. And that's kind of the end of it. That's kind of where we are at now. We have our SYNOPSIS core library. I have an F prime implementation that we're working on. We're just starting to work on a CFS implementation with some colleagues from the IB&B Center that are somewhere in here. They're there. They can answer questions about that. Where, like I said, we're targeting Class D mission deployments, probably in that TRL3 range. That QR code brings you to our website if you want to reach out. We have a preprint of a publication that kind of outlines the nitty gritty of some of this that I didn't want to go into here, but read the paper if you're interested there, or reach out to me. Happy to chat about it. The code's also open source. I don't know why I forgot to put that on there, but we're out on I believe it's the NASA AMOS GitHub repo, and I can provide more information on that for anybody that's interested. And definitely reach out if you think you have a mission scenario where this may be useful, or recommendations for the team on how we may proceed to kind of bridge that gap with the flight software community. That was all I have. Thanks.